Welcome to our lecture online. And the next topic in thermodynamics is the efficiency of a Carnot engine. Now, Carnot was a French physicist who understood thermodynamics quite well, and he looked at a thermodynamic cycle. And the one I have drawn up here represents a Carnot cycle, where you start over here at volume 1. You compress the gas isothermally, so no change in temperature. Then you compress the gas adiabatically. Then you allow the gas to expand isothermally, and then you let the gas expand adiabatically. And when you have a cycle like that, existing of those 4 thermodynamic processes, you have what we would term a Carnot engine. Now, a Carnot engine is not a real engine. You can't go out to a shop and build a Carnot engine. It's just a theoretical model of an engine that would, if it was built, have this as a thermodynamic cycle. And of course, the work done is the area inside this cycle right there. Can't build an engine like that, but Carnot was able to prove that the efficiency of an engine, if it was built like that, is the maximum possible efficiency you can get out of an engine under those thermodynamic processes and under those temperatures. Now notice that this here would be T cold for this isotherm, and this here would be T hot. And so Carnot realized that the efficiency of an engine was determined, or at least bounded, by the temperatures at which this engine operated. The temperature at which the heat was received and the temperature at which the heat was expelled. And he realized that the larger you can make that difference, the greater the efficiency was. Now, normally, an efficiency of an engine can be defined as the work done divided by the heat received from the hot reservoir, and this can also be written as QH minus Q cold divided by QH. QH, of course, being the heat we receive from the hot reservoir, and Q cold being the heat being expelled to the cold reservoir. The Carnot efficiency, so we can write E sub C, which of course is that theoretical engine, the one that really doesn't exist, is equal to T hot minus T cold divided by T hot. Now notice the similarity between these two equations. Here we use Q, here we use temperature. And in all circumstances, the efficiency is always less than or equal to the Carnot efficiency. There's no way an engine can ever have greater efficiency than the Carnot efficiency, which in other words, the efficiency of any engine is always less than or equal to T hot minus T cold divided by T hot. And if you then plug that part of it in, you can always say that Q hot minus Q cold divided by Q hot, which is the efficiency calculated for any engine, is always going to be less than or equal to T hot minus T cold divided by T hot, or the work done by any engine divided by the heat received from the hot reservoir is always going to be equal to less than or equal to T hot minus T cold divided by T, and I should say T hot. I got this wrong here. This should say T hot. I hope I don't have it wrong anywhere else. No, I was correct there. So this is what Carnot had decided. Well, he didn't just decide it, he actually proved it mathematically. And in the later video, I will repeat that proof. So if you're interested, come back and take a look and see how that was actually done by Carnot. But all we need to know to solve these types of problems is realize that there's an upper limit as to how efficient an engine can be, and that's determined by the temperature at which we receive heat from the hot reservoir and the temperature at which the heat is exhausted to the cold reservoir. And you can imagine, if you want this to be large, then all you have to do is make T hot larger and T cold smaller. And of course, in the limit, what do you think T cold would have to be for the efficiency to be 100%? T cold would have to be 0, so T hot divided by T hot is equal to 1, which is 100%. But in other words, Carnot realized, and he proved, that the maximum efficiency obtainable, or actually the second law of thermodynamics says you can't obtain the 100% efficiency, but the only way to get there close is to have Tc approach 0. And of course, we know there's no way you can take all of the heat out of the exhaust before you expel it out to the atmosphere. Matter of fact, what happens to a gas when you cool it down to near absolute 0? Well, it first turns into liquid, and then if you make it colder, it turns into a solid. So you would have to expel solid cubes of gas in order to make the engine almost nearly 100% efficient, and of course you know that that would not be possible. So there you go. That's an introduction to the Carnot engine and the Carnot efficiency, and I'll show you some examples on how to utilize that.